Hello everybody and welcome to NPTEL online certification course on cryogenic electronics for quantum computing. This is lecture number 35 and we will be looking into the effect of cryogenic temperature on leakage and saturation current. So, the outline of this talk will give you an idea about the leakage in long and short channel devices. We will understand what is saturation current and the crossover point in current. So, typically why this lecture is important, first of all you should understand that please understand that these devices, when they are integrated in form of circuits and they are required to be operated at relatively very low temperatures around 4 Kelvin or even up to millikelvin, the power budgets are very stringent, right, which means that the amount of power which the device can dissipate should be very much restricted. And the reason is that you need to maintain such low temperatures and therefore, the heating within the chamber should be minimized to a larger extent so that the cooling is proper and you are able to reach to a temperature where the requirement is there, which is around 4 Kelvin or so. It becomes more stringent as you reduce the dimension of the device, right. So, typically the reason for this is that your power dissipation is a critical aspect within a system. Now, this power dissipation consists of two parts. One is a dynamic power, which basically means that when the device is actually operating at, let us suppose, say some frequency, say if you at the order of few megahertz or gigahertz, there is always a charging and discharging of the capacitor which results in this dynamic power dissipation, and they become a function of frequency of operation, they become a function of the applied biases which you see, and these are quite sort of biases which are very low at sense. The second aspect is basically your leakage. Leakage currents are basically those currents when your devices are primarily in the off state or your devices are kept at a very low VDD, almost near threshold voltage, and ideally you should not get any current output in the threshold voltage, but even at such a low temperature you will start getting some leakage currents, and that is the idea. We want to study this leakage current. So, when you plot I versus V, right, current versus the drain voltage, you will see for any FET device you will have such type of profile, assuming there is no channel length modulation effect. Then we define this voltage to be as the saturation voltage, where VD sat, right, is approximately equals to VGS minus VTH. This is referred to as overdrive. So, VGS minus VTH is basically the overdrive. So, when your drain to source current is exactly equal to that, the pinch off takes place for a long channel device in a bulk MOSFET. So, that is the saturation current sort of origin which happens. Why long and short? Because the saturation point and the behavior changes for both the two types of devices, right, for the long and short, because in short the effective electric field is in 2 dimension, whereas in a long channel device the effective electric field is along 1 dimension. And that is the reason why threshold voltage modeling is important, because if you are able to extract the threshold voltage, then you know that gate voltages which are lower than the threshold voltage will have leakage currents, gate voltages higher than threshold voltage will result in saturation current, and that is more so the reason why you want to model the threshold voltage effectively at lower temperature. Now, let us look at the graph which is kept on the left hand side, right. This is coming from a threshold voltage model, and so this is your linear mode of operation and this is your log mode of operation and this is a linear mode of operation. If you go from light blue further towards higher temperature, you will see that the effective threshold voltage goes on changing, right? And we have seen this in our previous slide also. However, quite interestingly, there is a crossover point somewhere around here, around the threshold point 0.5 to 0.6, where you will see that lower temperature or cryogenic temperature current suddenly becomes larger as compared to that of the drain current at 300 Kelvin. So, if this is my, let us suppose 300 Kelvin and this is my 4.2 Kelvin, let us suppose, then below threshold 4.2 Kelvin shows you a lower current, whereas as you cross the crossover point, the threshold voltage or the current related to 4.2 Kelvin that shoots up very fast, whereas that with 300 Kelvin shoots are very small. And therefore, if you look at the threshold voltage is basically extrapolating this backwards. You will see the 300 Kelvin threshold voltage is relatively smaller as compared to that of the 4.2 kelvins. So, which effectively means that there is for sure a threshold voltage change. When there is a threshold voltage change, everything in this domain, right, for 300 Kelvin is basically my leakage current. And if you talk about this, around 0.5 is basically the leakage current at 4.2 Kelvin, and this is at 300 Kelvin. So, at 4.2 Kelvin, you will at very low temperatures, threshold voltages tends to increase in that sense, but there is surely a crossover point happening around 0.6, 0.7. And therefore, when you study the threshold voltage, you know how much amount of reduction in the leakage current has to be ascertained. So, let us look at the leakage current in long channel devices. When I say long channel, I mean to say the length of the device from source to drain is much larger as compared to the collision path. So, typically channel lengths of the order of say 1 micron or even 180 nanometer or 350 nanometers, 0.35 micron. These are all standard long channel devices. Earlier, much earlier, about 3 decades earlier, about 2.5 decades earlier, you had channel lengths of the order of few micron also. So, typically of the order of maybe 1 micron, 5 micron channel lengths were available, which has now come down to nanometer and even to angstrom lengths. What we are looking into is, can we predict the leakage current for a long channel device? Now, the idea here is that we are concentrating only on the cryogenic temperature, which is 77 Kelvin or around 4.2 Kelvin, which we are referring to. Here, the thermal energy, which is kT by kT, and if you want to convert into voltage kT by Q, drastically goes down, and as a result your intrinsic carrier concentration actually goes down. So, the intrinsic carrier concentration at 300 Kelvin is about approximately 10 to the power 10 per centimeter square, and this goes down several orders of magnitude lower and lower. That is one thing. The second aspect which you need to understand is that at such lower temperature, there are very few thermally generated carriers, right, and therefore this results in a much lower leakage, right. This is a very important point to note, that the thermally generated carriers are very small in number. There are much fewer thermally generated carriers available. And why? Because in any case your temperature is so small that you are not able to predict the thermally generated charge carriers, right, and that is the reason you will have a much lower number of Ni or in electron hole pairs being generated. So, finally, the EHP generation which will happen, electron hole pair generation, will be very small at cryo. Not only the generation will be small, however, there will be also a case where the recombination will also be reduced to a drastically low value. But one thing is for sure, that at cryo your leakage currents will be relatively very small as compared to a large channel lengths, right. So, this was the basic idea behind the leakage current at the long channel as a long channel device. Now, let us look at the subthreshold leakage, and the subthreshold leakage is given by this formulation, where I sub, the subthreshold leakage, is equals to I naught, which is basically the current without taking into consideration the subthreshold leakage multiplied by exponential Vg minus Vt, the overdrive, divided by n times Vt, where Vt is the thermal voltage kT by Q, and n is a subthreshold slope factor. So, n is a subthreshold slope factor, Vgs is the gate to source voltage, IO is the pre-factor depending on device geometry and mobility, and it depends upon many factors, for example, the structure of the device, the bias of the device and so on, and Vt is kT by Q. Now, you need to understand that as threshold voltage tends to increase at cryo, the overdrive term Vg minus Vt tends to decrease, right, and therefore your subthreshold leakage is reduced, right. So, let us look in this manner, that when you reduce your temperature, since your cryogenic threshold voltage is larger, then the overdrive reduces, and therefore your I sub, which is the subthreshold leakage, right, subthreshold leakage is actually very low, and that comes as savior in terms of power dissipation naturally. So, this is nothing to do with any of the changes which we are trying to do on the leakage path, but ordinarily just by looking at the value of VGS minus VTH, you can actually find out the value. So let me name this as VTH because there will be confusion here. VTH is the threshold voltage, and VT is KT by Q, which is 25 millivolt at 300 Kelvin. Now you need to look into another important aspect here, that is I naught also consists of the term of device geometry and mobility, right. And so if you remember in our previous discussion also, we had seen that the current is a direct function of mobility, correct, and mobility is also a direct function of temperature. So the subthreshold current will be a function not only of the overdrive, which is VGS minus VTH, but it will also depend upon the mobility of the charge carriers. We will come to that as we move along. N is a subthreshold factor. For all practical purposes, let us assume this to be equals to 1, and therefore I will get I sub to be equals to I naught exponential VGS minus VTH divided by VT. VT is a fixed value, 25 millivolts I can give, millivolts I can keep at, this is at 300 Kelvin, please understand. It will become very low at very low temperatures, KT by, so it is KT by Q, right. So I need to point out this as well to you. We are assuming the threshold voltage is increasing fine, therefore the numerator is decreasing, but you also need to find out that your denominator is also decreasing because of the drop in the temperature. So at 300 Kelvin we know that it is 25 millivolts. Please find out what will happen at 10 Kelvin, very straightforward, KT by Q you can find out, and from there you can find the value of the value of your N times KT. So if it is 300 Kelvin and if you reduce to 10 Kelvin, there is a decrement of approximately 30 times, and therefore your thermal voltage will also decrement by 30 times, and the denominator will reduce by 30 times, means the overall will increase by 30 times, and therefore I sub will be not so low as you would expect to see just because of the threshold voltage variation. So please keep this in mind, that the I sub is now dependency on not only threshold voltage, but also on the thermal equivalent voltage. I have still not considered the IO value in all these cases. Now let us look at the short channel. It is almost the same as long channel, but quite interestingly, and this is where the interesting part comes into picture, there is no sort of crossover here in the short channel. If you look very closely on the left hand side graph here, so if you look, this is basically a channel length of approximately 1 micron here, and W is 100 nanometer, this is width, right. And if you go one step further, this is 30 nanometer, from 1 micron to about 30 nanometer. And what we find out, look at the linear scale, which is the right hand side scale, there is no crossover here incidentally for short channel, right. The threshold voltage for this is relatively larger, 0.6, whereas at 300 Kelvin this goes to below 0.5 as well, if you extrapolate it backwards, constant current. And one important point we will see later on is, if you look at the slope of the curve and you try to find out the subthreshold slope, right. If you remember, the subthreshold slope by our primary definition was the amount of gate voltage which you need to give so that there is a decayed change in the drain current, right. That is the whole idea of a subthreshold slope, right. And we know that at 300 Kelvin the subthreshold slope ideally cannot go below 60 millivolts per decade. So my SS cannot go below 60 millivolts per decade, right, at 300 Kelvin. However, that is not true as you go down, right. As you go down, the subthreshold slope tends to become smaller and smaller, and that can be seen from this particular idea. You see, if you see the slope of the blue curve and the red curve, dark red curve, there is a difference, which means that the 4.2 Kelvin subthreshold slope is much varying as compared to a 300 Kelvin slope, right. And in fact, the blue colored slope is relatively larger as compared to that of the IDS for that of the 300. 1 upon slope is your subthreshold slope, and therefore relatively smaller value of subthreshold slope you will get for reduced value of temperature, which means that at reduced value of temperature, if you take up a short channel device, right, then the switching of the short channel devices will be much faster as compared to long channel devices. Whereas, let me go back to the previous slide. If you look here carefully, here also the blue colored curve gives you a much steeper curve, right, and red colored is relatively smaller. But if you closely look at it, since there is a crossover point at the exactly at the crossover point, the slope will be exactly the same. But if you therefore operate your gate voltage, which is the signal giving voltage, above 0.6 or below 0.6 approximately, you will see that the subthreshold voltage is much changing. Beyond threshold, right, when you go beyond threshold, you see the blue color slope is much higher, and when you go to below threshold, the reverse is correct, right, and then you can predict therefore the subthreshold slope will go on changing beyond a critical point. Now let me come to the saturation current. So we have dealt with two things. We have dealt with how a subthreshold changes and how does the threshold voltage changes. Let's look at the saturation current in a long channel device. This is the saturation current, right? Now this is ID VG, but if you plot ID versus VDS, the drain current source, what you will get is basically under no CLM you will get something like this. This current is ID sat. The current where, assuming that this is a constant current source, where you get VD sat, the current is ID sat, right. So if you have at reduced temperature, if you have increased carrier mobility, the current will be obviously higher because your I naught will be higher in that case. Moreover, at reduced temperature, since the scattering is small, you will always have a lower series resistance. Similarly, since the thermal energy is small, your lattice vibrations are relatively small. Further, if you further go on reducing the channel of the device to say nanometer or even below nanometer, I might get a ballistic transport region. What is a ballistic transport is that, so ballistic transport is something like this, that if you have lattice points here, an electron is coming and striking it, and then it will scatters here, and then it scatters to the next lattice point, then this is the average scattering length. If your device dimensions are less than the average scattering length, we define that to be as the ballistic transport, primarily meaning that the devices can reach even technically, theoretically, even from source to drain without suffering from a single scattering event. This means that your mobility is effectively very high in that case, right. So let me again rephrase my four important terms you need to keep in account when you are actually working with long or even short channel for that matter. There is an increased carrier mobility, much lower series resistance. There is a huge suppression of lattice vibration, so the scattering parameter reduces, which results in the mobility increase. Similarly, ballistic transport region in nanoscale devices where the dimensions of the devices are very small, it is primarily ballistic transport, which results in almost a very large increase in the value of mobility. Typically, therefore, the whole thing arises that the current increases, and that is what you see here when you do this. You see the current is actually much larger at post threshold for a long channel, even a long channel device, but with a reduced value of this thing. Let me come to in a long channel device. So as I discussed with you, we will elaborate on it. We had a phonon scattering limited mobility, and therefore they are reduced at low temperature, because at low temperature the phonon scattering reduces drastically, and therefore this increases the carrier mobility, right, especially the electron, but that is true for holes as well. Now since the current is proportional to mobility, the current also tends to increase, right. The current tends to increase to a larger extent in this case because of the increased carrier mobility. Now what happens, and this is quite interesting, maybe we are discussing this for the first time, but nonetheless it is discussing. It is interesting to look at. Look at the first point. See, if you look at the structure of any MOS device, you have source and drain here. However, there are contacts, metal contacts, which are sort of a buried contacts within the source and drain, and these have contact layer metal lines which are there, and these metal lines carry to the layer 1 or layer 2 level of interconnect. Now the resistance between the contact, which is this black colored knob here, and the source drain, this is basically a metal semiconductor contact, right. This is not a pure ohmic contact, but it is a non-ohmic contact. And if I assume that the contact between the source and drain region actually reduces at cryogenic, because the electron phonon interaction becomes much reduced. What is electron phonon? Phonon is by virtue of thermal, and electrons are by virtue of electrical biases. They tend to become much less combined set. The reason is, as you lower the temperature, the phonon interactions are much reduced. Moreover, the electron, just because of thermal variations, do not change its position too much, and therefore there is a reduced electron phonon interaction, and therefore the contact resistance actually starts to reduce, and this is known as a source, drain, contact, series resistance, right, implying that the current will increase. And that is the reason, the last point, that more current is allowed to flow with a relatively less voltage drop across the contacts. So, we are looking at a less voltage drop across the contacts and more current is allowed to flow as such. Now, as I discussed with you, suppression of lattice vibration primarily means that since the vibration is reduced, the mean free path improves or becomes larger, right. And therefore, it is something like this, like if you are moving across a room full of people, your average mean free path will be low and your velocity will be small, because you will be striking with larger number of people per unit length you cover as you move from one end of the room to another, right. Whereas, if you actually reduce the temperature drastically low, since the lattice vibrations have reduced, the probability of scattering is reduced, and therefore, the mean free path is much longer, which means that the velocity of the charge carriers are higher, and which therefore means that there is an efficient carrier transport. So, in the last statement here, there is an efficient carrier transport. Why? Because you are allowing the device to move faster in this case. I had already discussed with you the ballistic transport phenomena in nanoscale devices, and this means that this goes without scattering, and this boosts the saturation current. This we have also studied. I will just quickly go through it, that in nanoscale devices there is also a problem of what is known as a backscattering. When you do nanoscale devices, either there are a large number of papers or studies which do a ballistic transport or even quasi ballistic transport, and the current is limited not by mobility but by the injection velocity, right. Injection velocity is the velocity by which the electrons are injected from the source side into the drain side, and there is also a level of backscattering, which backscattering basically means that if there is a 180-degree shift in the direction of the charge carriers because of lattice vibration, we define that to be as a backscattering. At cryogenic temperature, obviously the mean free path increases, already discussed with you, but the backscattering dominates at the source channel barrier region. And so there are two things which play opposite. One is the mean free path increases, and therefore I would expect to see my injection velocity becoming large. At the same instant of time, my carrier backscattering increases, and therefore the velocity in the opposite direction increases, right, and therefore that reduces the injection velocity to a larger extent, right. So that is the reason the saturation velocity or the saturation current does not increase as much as we want it to increase, or theoretically predicted increase is not that large. So, let us look at the injected limited current model. We have already seen it, where B is the backscattering 1 minus R, R is the probability of scattering, and the backscattering doesn't improve significantly at cryo, and that limits the current increase, right. If you remember, when we were discussing basic even in your BTech first year, second year, when you are told to study devices, this BSAT does not come into picture. BSAT comes because of the backscattering coefficient, and that is available to you at very low temperature, right. And therefore, as the value of R goes on increasing, BSAT goes on decreasing, right, and therefore higher the value of R, your BSAT will go on reducing. Similarly, as you will also have the second point, you will have reduced inversion charge as the threshold voltage increases. Why? Because Vg minus Vt, the overdrive reduces, and therefore the number of inversion charge is less, and therefore the current is also small in that case. So, two things we need to account in, at least from this slide. One is the injection limited current model is valid, backscattering comes into picture, which tries to reduce the injection velocity, and your inversion charge threshold also increases, thereby reducing the current. Now, let us look at the final point, which is the crossover point. The crossover is seen because of two phenomena, which is dominant at low temperature, while the other is dominant at high temperature, right. So, this is the crossover point, this dotted line is the crossover point. Below the gate voltage around 0.6, 0.7, threshold voltage is dominating, right, and therefore the current with low temperature actually shows a relatively lower value for the same gate voltage, while after Vg the mobility factor becomes lower for higher temperature, it becomes higher for lower temperature, and that is the reason the blue curve actually exceeds the red curve, which is for 300 Kelvin. So, two things happens below the crossover point, it is primarily mobility dependent term, but other things comes into picture. Beyond the gradient, the mobility term actually dominates for low temperature, and the current suddenly shoots up because of that, because it is directly proportional to each other. Let me come to the last point. Therefore, if you look at high temperature, when we look at short channel devices, such crossover does not happen, right? I will leave as an exercise to you why it does not happen, but you think about it. These crossovers are only visible in long channel devices, they are not visible at short channel devices. Does it mean therefore that the mobility function of temperature is not very strongly seen in short channel devices, right? Just think about it, and you can have this, you can look at these papers by Beckers, and you can have a look at it and get an answer from here as well. So let me recapitulate what we did for the last half an hour in this lecture. We tried to look into the various scattering mechanisms, right, and how does it influence the threshold voltage and the mobility. Then we looked into backscattering and the backscattering. Then we looked into what is known as a ballistic phenomena, right, and then we looked into various scattering, and then the crossover point for the long channel devices, and what is the reason for these crossover point to happen, and which is not available in the long channel device, right. So just think about all these things, and I hope you enjoyed this. When we meet next time, we will take care of the remaining part of this lecture. Thank you very much.